Okay, good morning. I can just about say good morning. He didn't overrun far enough. Okay, so I'm Andy Williams. I'm one of the Siemens application specialists, one of several who cover the country. And today I'm just going to do a short presentation for the next 45 minutes on the PROFINET and designing for performance. Okay. So between me and Dave, we are the guys currently standing between you and lunch. So we'll try not to overrun too far. Let's start with a nice video. Thanks for your time. That's my presentation done. Okay, you got to have a cheesy video to for some nice fun music to start off with. Okay, let's get back to the fundamentals though. Okay, so we've heard a lot about PROFINET, talked about this morning, but this presentation really is rolling it back to its roots and thinking about the installation requirements. So let's start off with PROFINET and its cabling technology. So we're moving away. So I think I heard before some people have been using PROFIBUS. Some people are coming from other networks. Maybe those networks are RS485 based. As we've heard many times today already, PROFINET is based on the Industrial Ethernet standard 802.3. We use Industrial Ethernet cabling, so Ethernet-based cabling, in order to transmit between devices from our controller. This typically runs at 100 megabits per second as a maximum, and does both the sending and the receiving down through the both twisted pairs that are in our system. The way PROFIBUS is slightly PROFINET is slightly different. Is that of course it is wrapped up in a TCP frame, but the actual protocol itself, the actual telegram for PROFIBUS is the same as PROFINET. The only difference is the way it's transmitted and the wraparound of the TCP frame. Okay, so some of the other benefits, what we would typically have with a PROFIBUS system is it would be a line topology, one I/O controller on any one network, along with its I/O devices. When we talk about the PROFINET network, we can have multiple I/O controllers, multiple I/O devices, all sitting in the one network. Now this does bring some challenges, which we will talk about later on in the presentation. But typically, the PROFINET devices are also, because they're based on Ethernet, they go through switches, and we've heard this talked about many times today, and the use of managed switches. Some of the benefits of this over PROFIBUS is that the transmission is sent from one device onto another. If that information is for that device, it will be received at that point. If it's not for that device, it will then be forwarded on to the next switch point and further down the line, as you can see there on screen. So the right switches and the right information is going to the right place in the network once the network is learnt. What that does give us a benefit is the diagnostics. So each and every managed switch and information or our I/O device or whatever it is in our network all has the capability to feed back our diagnostics. So this can be received, this information can be received with our engineering tool, let's say TIA portal has been referenced a couple of times today. Once it's opened, of course, it might be a little slow for you. It can be looked at in those types of devices, but also we've heard about network analyzing tools as well, and other external devices or softwares which can be used to analyze and fastly diagnose an unhealthy system. Okay. Now, we've got lots of capabilities on how we can actually control, connect our systems together. With Profibus, typically, it will be a line topology, or many networks will be a line topology. Profibus could actually also be used with OLMs over fiber, if required for longer distances, but you wouldn't typically see that very frequently. When we look at some of the topologies that are available for us in the world of PROFINET or industrial Ethernet, we can use line topologies to emulate exactly what we would have had in the Profibus world. We've got star topologies as well. So yeah, I have to be very careful between the differences between an RS485 based network based on Profibus. With the radial circuit on that, each and every cable goes through typically a connector. And when you unplug that connector, it doesn't disrupt the next device, the forwarding packets of information going on to downstream devices. When we do that with PROFINET, if a device powers down, if it's got no power, it can't transmit the signal onto the next device, okay? So it interrupts the signal. So in these instances, we may want to consider star topologies. We send the information to a switch, and then we use the switch to star out to devices. Okay, so then we start thinking about the availability. And the availability can also be improved with things like ring topologies. So this is where we take a line topology, and for one extra cable, we can wrap it around. Okay, so now we're sending the packet of information round, let's say clockwise in this instance, round this ring. What this ring is then doing, the ring manager is sending out test telegrams, looking for the ring to be in a healthy state, and the test telegrams coming back to the ring manager. Now, if those test telegrams do not come back to the ring manager, what will happen is the ring manager will then broadcast its information in both directions around that ring, trying to recover and communicate to as many devices as it possibly can. Once test telegrams are received again, of course, it will then self-heal and then reconnect and go back to its normal route. So this is how we can improve availability. And of course, with PROFINET, other options are available as well. I typically, rule of thumb, would design a cable-based system. This could be fiber, could be copper, but there may be instances where you have to get this information to places which are more difficult to reach, in which case wireless is also a possibility as well in these type of networks. We mentioned ring topologies. So the ring protocol inside the PROFI standard is MRP. MRP is Media Redundancy Protocol. Now, when we were talking about ring topologies on the previous slide, the ring limitation of devices for the MRP standard is 50 devices in a ring. So we're not talking about 50 I/O devices, just the devices that appear within inside that ring. Okay? This can be a limitation, but now pretty new to come through to the PROFI standard is the capability to do multiple MRP rings. And whereas we could connect them together before, now we can redundantly connect them together with MRP-I switches. So this is effectively where, and I'll come over here to point, this ring is linked to this ring with these pair of switches, okay? And if this link was to fail, this is basically configured and set up as an I interconnect, an MRP-I interconnect, and they would then pick up and make a new connection until the other one had recovered. Okay, so now we can connect multiple MRP rings together to make much larger systems. But this does come with a warning as well. Remember, PROFINET is quite high bandwidth utilization as well. So we need to make sure that we are designing our network and factoring everything properly and taking everything into account. So, I'm going to make a few references and comparing Profibus and PROFINET together. In this instance, there are many, many differences, but in terms of networking, PROFIBUS RS485 based. And effectively, there's a few things that would determine the speed of the PROFIBUS network. Now, in PROFIBUS, it is a common network, okay? So all devices have to communicate at the same speed. This basically means that the speed there's many, many things which calculate this, the network speed of your PROFIBUS communications, okay? The biggest one is the speed is the speed versus the distance that you wish to transmit the signal. Typically, the further you go, the slower you have to run, okay? And the other thing the big thing that would happen, also limit it, is the slowest device or communication device on your I/O network would also limit it, okay? You can't go faster than any one device can handle. In terms of PROFINET, I think it was Peter pinched a couple of bits of information from my presentation earlier on, so we'll just cover that in a little bit more detail. So we can see the PROFINET variant and the way that's set up on the left-hand side there. So a typical PROFINET I/O controller would send out clocks every 1 millisecond. This is PROFINET RealTime, and I will come on to the differences of PROFINET a little bit later on. So the PROFINET RealTime controller is clocking out at 1 millisecond, and then what we would do with each and every device is we would decide of that factor of 1 millisecond how often we want to subscribe to and read and write I/O data. Okay, so this is actually TIA portal settings, but every tool would fundamentally use the same techniques. So what we're saying is we want to update this piece of I/O cycle on here at 2 milliseconds. There might be another device where we say, well, actually, I want this device to talk faster or slower for whatever reason. And again, the point was made earlier, don't make things communicate faster than is absolutely necessary. Some things need to talk fast. Things like if you were doing drives and those drives had to be synchronized, you might want those to be talking very fast. There might be a piece of I/O sit on the other side of a wireless network. Well, that might need to be slowed down to cater for the lower bandwidth over a wireless network. Okay? And then the other value that's sat down here at the bottom is the watchdog value. So it basically does a mathematical calculation of the update time versus the number of allowed missed cycle times, which then gives us our watchdog factor. So as Peter pointed out earlier, the defaults are 2 milliseconds, 3 missed times, 3 missed scans, and that gives you a watchdog of 6 milliseconds. So this particular I/O device would effectively lose control of connection with its controller after 6 milliseconds and report failure. Okay, so differences between the different versions of PROFINET. So we start out with PROFINET RealTime. Okay, so what is PROFINET RealTime? Again, we mentioned on the previous slide, it is clocked at 1 millisecond. Okay, so this is the controller driving out a bus signal at 1 millisecond. And really, it's all about looking at this graphic down at the bottom. Now, we have our controller, which is reading our inputs and writing our outputs. And these could be local inputs, and these could be inputs and outputs or devices which are sitting across a network. That network is clocked. So we've got a process which is effectively reading our inputs, going through our code, writing our outputs to wherever they may be. And then what's happening is we are then sending that information out over the PROFINET network, finding those devices. And those devices could be low-level I/O devices, they could be drives, they could be intelligent devices, there could be all sorts of stuff going on there. And each one of these devices is effectively running its own cycle. So now we've got multiple cycles going on here. So just to wrap up, we've got the PLC running its cycle, we've got the PROFINET running its cycle, we've got the devices running their cycle. Okay? These cycles are not synchronized together. Okay? So I made a reference before about motion control. So we can do motion control now over PROFINET, where the actual motion control objects are done inside the PLC controller, not inside the drive. So we need this network to be more deterministic. And we're referencing here the jitter. So the jitter in this particular network, PROFINET RT, would be Well, in one particular cycle, the application code is cycled, and maybe it just gets its right information perfectly in time for our PROFINET cycle, and it just arrives at a perfect time. And then the PROFINET communication hits our device cycle, and that hits it perfectly, and everything runs absolutely seamless. The next time the information is sent, the application cycle might miss the PROFINET clock and have to go around again. And then the information then hits the PROFINET cycle, okay, then hits the device cycle, and the device cycle might have just missed and then clocked round. This is what we determine as jitter, okay? And in a high proportion of PROFINET installations, this is not a problem. This doesn't make any difference with the speeds that we're talking about when we're talking to just standard I/O devices. But when we're doing things like PID loops, very fast PID loops, or motion control, where we might have multiple drives on here, and these drives are running synchronous axis, and those synchronous axis are controlled from our PLC code, we need to effectively make sure that we don't have that jitter. Otherwise, we start having drives which are supposed to be electrically locked together, not becoming quite electrically locked together. Okay?
Just one thing, just out of ignorance, where is that PROFINET cycle time configured?
Okay, so that's configured in the firmware, in the software of your automation tool when you're clocking that out. So it is changeable. Typically, you wouldn't know. You would leave that clock out one millisecond. Okay. If you do have an application that then needs to be synchronized, so this will cover the PROFINET standard class A and B. Okay. We then move to what we call PROFINET IRT. So this is isochronous real-time. Okay. Now, this does allow us to run to lower speeds. So we can see on the screen there, we can get down as low as 31.25 microseconds. So more improved on our 1 millisecond. Okay. But it's not really so much about the speed. It's more about removing that jitter and making it more deterministic. And what we're seeing here now is we're actually, the isochronous real-time is synchronizing our PLC application code and synchronizing when it's reading and writing the outputs and linking them to our actual IRT PROFINET telegram that is being sent out to our devices. We then decide out in our field, these field devices, whether those field devices are going to subscribe to our PROFINET IRT telegrams. And they would synchronize their own processors as well. So they are now reading and writing information at the right times to synchronize to all of these together. And with all of this, what we're then doing is removing all of our jitter. Okay, so it's not necessarily so much speeding it up, which you can do. It's more a case of it is consistent. There will still be a time delay because this information still has to get from A to B. But what we're doing here is we're making it consistent every single time. Okay. The other thing that IRT also gives us is an inherent 30% bandwidth reservation. Okay. So it guarantees and makes sure that we have the bandwidth in the system in order to be able to do these higher speeds and synchronization. Then we get to the elephant in the room. You've heard it a couple of times today already, the non-real-time data. Okay, these are the bits where when we're merging our OT networks and our IT networks and all of the extra stuff, all the value add we get out of our products. So much of our edge devices, you saw some of the gateways being presented here earlier, they're typically programmed with things like web servers, okay? Intelligent devices, drives, soft starters and things like that, all having web servers in there which are providing information and data over the same cabling that our PROFINET system is running on. Okay. We could also be doing lots of Modbus, TCP, there's all sorts of stuff, OPC, various different non-real-time data which could be having an impact on our PROFINET network, which we really need to take account of. And you can see an idea, just as a very low-level graph, just to give us a kind of an explanation about the impacts of this, okay? And what I don't want people to take away from here is this is not a good thing to do. Non-real-time data is bad news, okay? It's good stuff. There's a lot of value add to be taken from this. We just have to think about it and make sure we design around it, okay? We can see there on the green line, hopefully you guys can make that out. It looks okay from here. We've got our RT and IRT data. Now, this is quite fast. There's a lot of telegrams going on, but the actual size of the telegrams are quite small. We're dealing in relatively small amounts of information. So the impact really is quite low on our network in a well-designed normal system. Okay. It's the other non-real-time data that we really have to take a look at. So we've heard about things like intelligent devices, IIoT data being transmitted, connections of ERP systems and things like that. Okay, all these have an impact on our network. And you can see there, some of them having a lot more impact than others. Video being particularly terrible for running in conjunction with a PROFINET network. You say, yeah, a lot of companies do have webcams on their system to machinery, part of machinery on the other side of a safety gate, which they need visualization on to bring back to their control desk. So they can look for things going wrong with the machinery without having to gain access. So there's lots of people doing this type of thing. But yeah, it is a terrible idea to merge them with a PROFINET network. Okay. Okay. So when we are looking at your engineering suite, you're putting the software together, you're dropping I think you saw a demonstration there from Pete before, where you're putting all your devices in your network and you're building your network, so whether it's PROFIBUS, PROFINET, whatever. The I/O controller and the engineering software suite of your choice can only know what you tell it. So you're putting I/O devices in, you're putting I/O controllers in. You might even be building, you might be fortunate enough to have an engineering package which allows you to do your HMI applications code in the same one. It only knows what you tell it, so it can only account for PROFINET real-time and IRT relevant data. Even when you put a HMI in there, it can't calculate it. It doesn't know what's going to go across that network. It's non-real-time, okay? It can't account for the impact, so it only knows what you tell it. Okay, so just a note, there's a few clever settings that you can make to improve it, but you need to be mindful of it. So with that in mind, what I'd like to talk about for the next couple of slides anyway, is the use of network planners. So network planners is a much better solution in order to make sure that we are designing our network properly and carefully with data-driven entry points, okay? And making sure that before we even plug anything together, even especially in today's world with a pandemic and components are difficult to supply and long lead times on most manufacturers at the minute, we want to make sure that the components that we ordered are suitable for the job. And we can do that a long way in advance with simulation tools, okay? Now, just to take a look at some of those simulation tools, if you go on the PI website, there are some free ones. You can get it from the link there, okay? If you go onto the website, just type in the calculation tool. This is a fairly manual approach where you can enter all the relevant network information and loading information, and it will provide you bandwidth information coming out, okay? Great tool, free to use. Please investigate that. There are other ways of doing it as well. Okay, so this is a screenshot from a tool that we use, and you can see it's a much more graphical representation of our network. Okay, we can see all of the devices, we can see the interconnecting cables, we can see every single port. Okay, so now we're really drilling down into analyzing what we're going to put in a long time before we necessarily need to actually purchase anything. Deep dive on what these tools can do. Okay, so we've got things like we've got reporting information in there. A big key one there is it can assist you in the validation of your PROFINET planning. Okay, so it does it can export reports, all the information based on all the everything that you put into it. It can tell you what all of your switch loading is, what all your cable loading is, and make sure that everything is suitable and fit for purpose. You can also use it retrospectively with the online scan function. So if you have a network, you can literally plug it in, browse a network, and as long as you're using managed switches, which we've heard several times today already, and all your devices support LLD, LLP, and DCP, then it can read back all of that information with an online scan function, and then you'll be able to see your network. Okay. If you've engineered with your engineering tool, we don't want to have to recreate all of this work twice again for you to have to rebuild all the hardware. So you do have the capability to import your project into this tool from your hardware configuration. Let's just take a bit of a deeper dive on there. So we're looking at a particular device on here. And what we can see is this particular switch on here. We can see that one of the ports is giving us some issue. This is port number 1, okay? And we can see that in a graphical view up there at the top, and we can see that also in a tabular view at the bottom. And we can decide which sort of data flows we want to include or exclude as well. So we can look specifically for non-real-time or real-time data, okay? Taking that scenario and just expanding a little bit further. So this is that switch again, but actually in its environment. And we look at this, we look at our PROFINET IO data. So we've got our controller here. I'm not sure if the pointer works. There you go, it does. Okay, so there's our CPU there. Okay, and that is talking PROFINET IO data to all of these devices here. We've got a whole list of them. And at the end here, we've got a PC running an application. Okay. And that PC application is also running TCP, standard TCP data, okay, along here. Now over here, we've got a load of other stuff where this port 4 is sending this information on even further. There we go. Okay, so when we look at what's going on in that switch, we can see our 4 ports. We've got 3 there on the left, and we've got our outgoing port, which is our problematic port on the right. And when we analyze that, we've got port 1, which is connected to our PLC, which has got primarily PNIO data going on to it. And port 2, we've got our network, which is fundamentally at the end of it got our IPC, and that's bringing some non-real-time data. Now, PROFINET is a prioritized application layer protocol, which means that inside its telegram it has a priority, which means that when it hits a switch, it is pushed into a different queue in some instances, okay, and it is prioritized over non-real-time traffic, and we'll see that here in this graph. So we end up with 2 queues, one queuing up the PNIO data, one queuing up the non-real-time data, okay? And these queues change dependent on the capability of your switch and the processing power of your switch, okay? Out of port 4, we get the PNIO data that arrived at the same time as the non-real-time data, and of course is prioritized. Then our non-real-time data will follow, and it will fit in between the clock cycles of the PNIO data, okay? It will always fit in, it will always be secondary. Now in this instance, we get a 35% queue/port load, okay, which is calculated based on our port output. So this is where our port is flagging us up. We'd like to see this under 20%, ideally, of utilization, which is why we're getting a warning on port 4 there, okay? If we take a slightly different application, we're going to see this, take this a little step further. So same sort of application. We've now got port 1 with PNIO data on and 2 ports with non-real-time data. And what we see is when the PNIO data floods in, we're filling up our queue, okay? And we're also filling up our secondary queue with our non-real-time data. So what's happening here is our queue has maxed out at 100%, okay? So what happens is, of course, as before, the PNIO data is prioritized and will be sent through before any non-real-time traffic to making sure it's clocked through, because this is our deterministic network. The non-real-time data will follow as and where it can. But of course, in the meantime, our PNIO data never stops. It's keeping coming in. It's deterministic. It's triggered by the controller. And that slips in. And then eventually we might get another packet through. Okay, our big problem here is now we've got too much other non-real-time traffic hitting our queue. And anything that doesn't manage to hit the queue in the switch and be processed will be dropped. Call it a dropped, missed, whatever telegram you like to call it, okay? It will not be processed, okay? And hence, you've now got a data packet with lost information. This might not be too important. It might just be one shot of a web server and it doesn't matter, you'll catch it on the next frame. But it could be a video, and now you're missing frames of video and things like that. It could be a very important piece of information that you really needed. Okay. So we have to be very careful on how we design our networks, making sure our switches are capable of doing it and looking at these tools in order to make sure our data gets to the right place at the right time. We can also use these tools in order to look at existing systems. So you might already have an existing system out there, but maybe it's not too late because these systems are being designed. We always get requests. So you've put an automation network in, now somebody wants to add a web server. They want to add IoT data. They want to put other stuff in, okay? They want a connection through to the corporate network and connect into an MES system. We're adding data all of the time, okay? So what is a good idea is, well, let's look at our system and let's make sure our system is capable now before we start adding anything else. Okay, so the tools can effectively, this tool in particular, we could use, we talked earlier about managed switches and the capability of having mirrored ports or even multi-mirrored ports, where we take the information that's received on the other ports where our networks flow, and through a spare port we make a mirror port. This mirror port is where we can connect a PC with something like Wireshark on, and we can receive that information. We can look at the data flows. Preferably, you would use something like a tap, which is a physical piece of hardware which sits in the network, which also gathers the same data. All of these devices, or these softwares, give us the capability to pull out what we call a PCAP file. And we've just seen there a PCAP file can be imported into the network planning tool. So now you've got your network diagnostic, your network view. You've got your PCAP file, which can then retrospectively put the real data in, not just the theoretically calculated data. And we can process that and apply that to all of the physical devices and how everything's connected. And now what we can then see in our tool is where any of the problems, maybe we're on the brink of a problem, we don't know, okay? But if we then start adding additional non-real-time data flows and things like that, we've then got somewhere to start from. Okay, so that's a little bit about network planning, but ideally we would do this at the design level as well. Okay, so we talked very early, right at the very beginning, my very first slide, about all the different topologies that were capable: rings, stars, lines, wireless, all this sort of stuff. Okay, what would be a real terrible idea is to say, I've got a really large plant, I'm going to put a nice redundant network ring in there, and I'm going to connect all of my O devices to it and all of my O controllers to it, okay, without even thinking about it. What we would much prefer you to look at doing is creating islands of automation, as we would like to call it. So here we've got two 1500 controllers. They're supporting their own lower level PROFINET I/O systems. This is a better design. We're now keeping that I/O traffic contained to within its own network and its own controller. And then what we're then doing is taking the controllers and connect them to a higher level system, which might be a ring, it might be various different architectures. But what we're now doing is we're keeping the PROFINET I/O traffic lower level, and then we're using the PLC as a gateway to transmit information in a northbound connection. Okay, and when I talked earlier about, or just then about having a ring and throwing all the I/O controllers on, etc., all into one network, this is exactly typically what can happen. Okay. So here we've got the two blue devices, so I/O controller 1 and I/O device 1. And then we've got the two orange ones, okay? So this is I/O controller 2 and its I/O device, okay? Now, they're just connected together with 3 simple bits of cable. Dead easy, dead straightforward, okay? Probably work in this application because it's quite small, okay? But it's just a representation of what can happen. So now what we've got is 2 I/O controllers, which means we've got 2 PROFINET networks. And those 2 PROFINET networks are now trying to get down the same industrial Ethernet cable. We've effectively now doubled our bandwidth utilization. Okay, we've got 2 1 millisecond clocked PROFINET I/O systems running down through the same cable. Okay, now in this instance, probably be okay. Okay, larger systems with more I/O devices, you're going to start running into problems. With a simple little bit of thought, it might just be that we threw it together and it was fine, but why not just reorder them in this case so as we don't have them overlapping. Now we have this I/O device talking to this I/O controller and this I/O device talking to this I/O controller and nothing going in between unless we choose for it to be. Nice little graphic showing good and bad. Okay. In a bit more detail, so if we were to look at that example and take that into our network planner, this is exactly what we would see. We've got 2 PLCs here, PLC 1, PLC 2, and we've got various different I/O devices sitting on both PLC 1 and PLC 2, so we've got overlapping areas, and same down here. What we can see here is we've got warnings on some of the ports. We can see as the further down the line we go, these warnings disappear and this device is actually happy and healthy. Because it is only receiving the information, sending the information to PLC 2. But then when we hit to this switch, this has now got this information, and this information is now going off down here. Okay, and same again, everything gets added and added, and eventually the bandwidth gets worse and worse and worse the further back to the main system we get. Okay, so we have to think about that. We've got the HMI also here with some non-real-time traffic sitting on there as well, because HMIs just talk TCP, they don't talk PROFINET, okay, or adding into the equation. So I mentioned earlier what we would tend to look at, what this particular tool looks at is we want everything to be under 20% utilization. That's going to give you a green. It's going to give you a green on your cables, green on your ports, okay? Anything between 20 and 50% is going to flag up as a yellow, and you really need to start thinking about it. If it's 21, probably be okay. Yeah, if we're hitting at 49, 50, then you really want to potentially consider adjusting your network design and making that better and improved. Anything over 50, pretty much well is unlikely to work. Okay, you're going to start having problems, lots of missed telegrams, and then you're going to be looking at your other tools in order to try to work out what's going wrong, because things will sporadically not talk to each other. Okay, another point to consider is the line depth. And this applies whether it's a ring, whether it's a star, however it's connected. We're talking about the number of devices, switches, whatever they are, between the controller and the I/O device. Okay, so we've got a controller here, we're going through a switch, then a drive, then through various other stuff, and then more drives and drives and drives. Okay, each one of these, whether it's an onboard switch of a device or whether it's a switch itself, each one of these is a switch. And each switch in PROFINET RT mode will have a latency, which has to be calculated. The further we go down, the more latency. Everyone will add more and more latency, and then this drive at the end has to report back, and the same latency is applied in return. Okay? So we must plan for this, and again, it comes down to, just like it was with PROFIBUS, we look at our clock cycle. So if we've got a 1 millisecond clock cycle, our nest in depth, number of devices we can go through, is 7. Quite small. Okay? At 2 milliseconds, 14. Up to 8 milliseconds, 58 devices. Okay, so thinking about how fast we need to run PROFINET IO devices becomes very important. We covered that earlier. Okay, if we go to PROFINET Class C, so IRT, the switch configuration changes to cut-through mode, which means there's less latency. There's still latency, but a lot less of it. Okay, which means that we get a lot better performance. 64 and then up to a maximum of 100, irrespective of how fast you're running. Okay. Okay. I couldn't possibly talk about the design aspect of PROFINET IO systems and not mention security. Again, with our merging IT OT worlds, we need to seriously consider all of this great capability that we have, but doing it in a cybersecurity way. So there's a new standard. It's been out for a while now, actually, but it's called 62443. This is the cybersecurity standard for industrial Ethernet networks. Okay. It sits under the umbrella standard of 61508, so it falls under a safety bracket. So whether it's a safety PLC or not, these threats are real, and these threats come in various forms. They come in forms of hackers coming in, manipulating your system. They come in the forms of denial of service attacks. We've seen incidents where hackers have gained access onto a system and deleted the PLC programs and held the company to ransom. All these things are possible, but please do not take this as a situation of, right, okay, I'm not going to interconnect my system. There are so many benefits to be had in the modern age that these systems need to be connected. Okay. Also, I will also add, just by air gapping your system and not connecting it up to your corporate network does not mean you are cyber safe. Okay. Quite the opposite. Okay. It does eliminate some issues, but also prevents others. So if you've got PCs on this network, you then got to think about, if I'm not connected, how do I patch manage those PCs? What happens if an employee comes in and plugs in a USB stick and has a virus on and deploys that onto my network, which is now not connected to a domain and cannot provide me with the virus protection, for example. So this is the standard. Please look into the standard. Please don't be afraid of it. It is a good thing to interconnect. Please don't take it away today that you would not connect these networks. We just have to think about how we're doing it. And this is kind of a wrap-up. When we're designing our network, we want to be thinking about the redundancy. Okay? Redundant networks tend to be more resilient. Okay? But only do that in the right place, the right circumstance. We should look at things like remote access. The pandemic has shown us that so many people have relied on remote access, but please don't throw it in without thinking about it and designing it in. A poorly installed remote access without firewall protection, without properly implemented security, like simple password protection for starters. And I'm not just talking about passwords of the remote devices, I'm talking about password protection in your PLCs, so system hardening is very, very important. These are great things to have. Through the pandemic, many companies have relied on it and has been a great win for them. Equally so, we've some horror stories in the press where these have been thrown in without thinking about it, and I won't go into details, but of course we've seen some problems that could have been avoided. Okay, when we then talk about also design of the systems, we should think about cell-based protection as well. Now, I showed you an image before where we had different controllers connected to a higher level network and running their own PROFINET networks. We can take that a step further, and we can think about protecting each and every PLC zone with their own firewall connecting back to the higher level network. Now we're putting in multiple layers of defense. You've got your corporate network, your corporate firewalls, you're then coming down into your automation network, and then we're doing firewall protection based on a zone. Okay, this is also a good thing to have, but don't just put them in willy-nilly. You've got to be thinking about it. I tend to look at a cell as either a machine. If it's a machine that runs standalone and can produce output by itself, that's a cell. If it's a line of which takes 5 PLCs all to run together, if you lose any one of them, the line is down, then that for me is a cell. Because those PLCs, you don't want to hinder the communication between those PLCs, but we want to protect the cell. Okay. There's some great literature on the PI website, which you should definitely take a look at. This one is a particular favourite of mine, the design guideline. It goes through many of the points I've gone through today and also expands on them an awful lot more into a lot more detail. It's free to download. Okay, this is an older image, so there's actually been updated since then. There's also another one for the installation guidelines as well, and many other ones to complement all of that. So make sure you're not just throwing cables in and not installing them correctly, and making sure that we are doing everything to give us a nice, strong, robust network. There's also another one there called Capture the Field Bus as well, which covers both PROFIBUS and PROFINET, which is also a good read, and that might be worthwhile the investment. One final thought, just to capture some of the stuff like Peter said earlier. When it comes to Ethernet switches, there are 2 types of people. Okay. I can absolutely categorically say that is absolutely true. And what I'll also say is, why have one final thought when you can have 2? When it comes to network design, there are again 2 types of people. Please don't be the latter. Okay. Okay, so thanks very much for your for listening to me today. I'm Andy Williams, Siemens Automation Specialist. I'm pitched over there. Don't have a tabletop demonstration today, but I won't ask for questions now, because in an open forum people don't like to do that. If you've got any questions or you want a deeper dive into any of this today or want to go any further, please come and see me over on the table on my table over there, and we can chat. Okay. All right, and I'll just pass you back to Peter. Thank you.